Okay, well, let's see. I want to do the harmonic wave, but we don't remember simple harmonic motion. Maybe we never really understood it, so we got to understand it now. Simple harmonic motion. Start at some angle phi. Move at angular velocity omega for some time t. Then this angle here is phi plus omega t. Let's pick one of the two possible coordinates. I'll do omega t plus phi, which is where we usually write it, is this. That's the equation of simple harmonic motion. Omega is the square root of k over m. The k here is not the same as the k here. That force is negative kx, and solve the differential equation, your omega will square k over m. There's your omega. Phi is just wherever you happen to start your timer, which might be at the instant you start the motion. There you have x, function of t. Of dv equal to y dt. That's most of what you need to know, most of the basics. Those are equations. Everything comes down to these equations. Now, there's more to this model. There's the tangential velocities and tangential accelerations, and centrifugal velocities and centrifugal accelerations. Okay? No centrifugal velocity, that's zero. Centrifugal acceleration. Okay. So anyhow, you got to know that. Using the meaning of omega. Now, using the sine instead of the cosine. I could have done this with the sine just as well as the cosine. Because then you would think, you know, that would be your motion along the y-axis instead of the x-axis. Okay. But anyhow, y equals a sine of kx. That's a graph. Looks something like this, right? Now, wavelength lambda. Okay, I was talking about the idea of somebody doing that thing with the ropes. So you're doing this with the ropes, getting the wave going. Okay. So, asking, you know, about what do you think lambda would be? So one wavelength Well, I'm not going to make this completely rigorous. And it should be fairly obvious. For one wavelength, how much does Kx change by from here to here? And we're going to stop a minute and maybe talk about that. For one wavelength, I suppose if they changes, I didn't write the end. I can't rescue it. So Kx changes by 2 pi. Okay. Now, if x changes by lambda, when Kx changes by 2 pi, then what's the value of K? I'm sorry, this chart is on the right. X changes by 2 pi, X changes by lambda. So what's K equal to? Okay, if Kx changes by 2 pi when X changes by lambda, so K equals what? Well, you answer that by saying K lambda equals 2 pi. And of course, if I give you the equation with K, and you want to find lambda, well, lambda is how much X has to change to get 2 pi here. So again, K times lambda is going to be 2 pi, and you do that in your head. Okay. Now omega is the same as it would be over here for simple harmonic motion. And the next question is, how is omega related to the frequency? Okay. Now we've reasoned out that frequency is like cycles per second. And omega is radians per second, right? So frequency okay, frequencies in cycles per second usually. It could be cycles per hour, cycles per millisecond, or cycles per nanosecond. It's usually cycles per second. That's a standard unit. And also, that's called hertz. After got it studied sound waves. So, that 1800, I think. 1800, I don't know. So F is in cycles per second. Omega is radians. So you got to think this. Okay. Omega is 2 pi F. Now, you reasoned that out. You got that. So you want to continue to get that. You don't want to forget how to get that. You want that to be your go-to relationship in frequency and angular frequency. So now you can just do it algebraically. Your frequencies will now go over 2 pi. And your period is reciprocal frequency. If the frequency is 4 cycles per second, then the period is 1/4 of a second. here's how long it takes to get around that circle, or how long it takes to complete an oscillation. I'm trying to move my hands, the camera's not on, okay, I'm too close to it. The frequency of the oscillation is inversely, well, just the reciprocal of the period. The period's a tenth of a second, then you have 10 cycles per second. That's obvious. These are obvious relationships. You don't want to try to do this by remembering formulas. You want to reason it out every time until you get used to how to reason it out. Again, the formulas are too confusing. Or which one has 2 pi, which one doesn't? 2 pi in the numerator, 2 pi in the denominator. Which of these is mean? You know, you get all confused. Okay, until you think about what they mean. Okay, so there we have that. Well, okay, so here's y equals a sine of kx, right? Okay, now what if we want to do? Sine of kx minus omega t. Well, it equals, it's a sine. We can write this as k times quantity x minus omega over k, right? I mean, I just factored out k. Now, if you don't believe me, multiply through distributive by the distributive law, and you're going to get this, right? And if that's not a familiar form of factoring, well, start getting familiar with it because it's important. Okay? Important symbolic manipulation. It's a simple one, but if it looks a little weird to you, I can understand, but you know, make sure it looks less weird next time you see something like that. Okay. Now, why did I factor it like this? This is important enough to write red, about close to red as we got. Times T. To the right. Basic transformation from pre-calculus. Which most pre-calculus teachers finally give up because students never will understand it. Okay? Now, students who are properly prepared for pre-calculus, if they have to learn pre-calculus, will understand this. Okay? And you guys have the aptitude to understand it. So make sure you do. Okay? But you probably got through pre-calculus without having to, even though you did it. If you did the course, as it's you know, like the 4th section of the book. Okay? Not early in the course. And textbooks that we're using, maybe a little later than others, but it's done fairly early in the course. Horizontal shifts, vertical shifts, stretches, and all that stuff. You got a vertical stretch here, you got a horizontal shift because of this, but you got a factor to get that. Well, that's supposed to be done in pre-calculus. But it's a tough, so students in this reading. Okay. That's necessary to understand in order to understand that this is the equation of a wave that's moving to the right. Now, what you have here is then that this wave moves distance. And there's no negative right there. It's all negative. So I wrote it down. It's not a negative. If you subtract from X, that moves everything to the right. I can tell you why. You just need to work it out. You need to get that. Okay, so what we have here is then distance omega t over k. The graph moves that part to the right. So every point moves that part to the right. So now the graph is going to look like this. And it's going to continue on. How fast then is this thing moving? So we're going to pause here and we're going to try to work that out. Okay, so still confusion because again, you couldn't understand transformations earlier. So you got to fix that. You need to understand those transformations. Period. Okay. Now this could be an ongoing wave that started way over here at some distant time in the past, right? So it's been moving, and here maybe it's an infinite wave, maybe it's been moving forever, and at t equals 0, and you choose when t equals 0 is. Here's why I start the clock. Start the clock when it's here. Could have started it when it's at some other point, but the picture is clear if I choose to start it here. Then of course you would have something like this here, and it would continue on here, but I don't want to mess up my artistic writing. So you just think of this as something that's been going forever, right? So whatever you start, if this is t equals 0, then this is where it is at omega t over k. Some short time later. If you want to do the long time later, maybe it's 7 miles down there, maybe omega t over k is 7 miles. Okay. In several cycles, thousands of cycles. Okay, thousands of cycles. But to illustrate it, we choose to assume that omega over t over k is fairly small. To see what happens in a short time. Whatever happens, it is going to shift by omega t over k because of this simple factoring. Okay, and the whole rule for transformations, which you should understand not just as a rule but for life. Okay, because that's kind of part of your mathematical toolkit that you're going to want to have. Okay, so then if we want to know how fast, we said, well, move this far and took time t. To move this far and took time t, then its speed was this far divided by t, and there's a t up here, divided out, and you get omega over k. Right? Okay, does that clarify it? Just nod. Up, down, okay. Yeah. Well, again, it's there in the video. You can find it. It's important, it's critical. It's a central idea. Okay. What the world is going on out here? We're going to have to trash somebody. Or is it just somebody having a fit? They can't help. I don't know. Should be going. No, I don't have to trash anybody, down to about 60%. Okay. So what we have here is, of course,
Where's that yelling coming from?
I'm sorry?
Where's all that yelling coming from?
I don't know. I just asked my class, am I going to have to go trash somebody? I came out in the hall somewhere.
Yeah, I want to create securities. I know something's going on.
I don't hear any yelling in response.
Okay. I want to make sure we didn't call reason.
Well, I don't hear anything that indicates that, but could be. I'd have to hear a little more.
I just make sure.
Yeah, I agree with you. Okay. We'll take care of them. We'll take that guy. Okay, anyhow, we got staples and leg overtake. That's where I was heading. That's a mathematical description of it. Traveling wave. It's that simple. And there's nothing in there that's terribly complicated. You just have to put it all together and keep the pieces in mind. Okay, digression. And the graph of x minus h is the same as the graph of f of x. At every point shifting. I'm going to say h units. In the x direction. Okay, that's the rule. Now, if f of x equals a sine of kx, then f of x minus omega over kt is this. But of course, we approach it from the opposite direction. Here we factored to get this form, so we would know that the graph shifted this far. Okay. Now, why does it shift in the positive direction? In vernacular, it's h, it's not negative h. That's got to be bigger. You give f of x minus h the same value. As f of x. In other words, if f of x equals 5 at some x, and f of x minus h is going to equal something else. If x is 7 units bigger, then it will be equal to this, and the points will correspond. Now, I'm not going to go any further than that. You need to think that through. But there's a reason for it, and you try to get the reason, which is good. I want you to know the reason, okay? And since you keep pushing for the reason, I'm going to give you a reason. But from that point, think it through, okay? And I'm glad to give you the reason. I'm glad you're pushing to get the reason, because much better off understanding reasons than formulas and rules. Understand why the rules are, and especially in the case of this stuff, which, as I said, has a bunch of confusing formulas. You're going to be confused by the formulas. Formulas have very simple meanings. Okay, you just want to understand those simple meanings so you don't screw them up. So you don't need to remember the formulas, so you know what to do. And of course, you understand the reasons, you can write down the formulas correctly. Why is there a 2 pi there? Well, it's because of radians and cycles, you know.
Recording in progress.
Okay. This is another harmonic wave. Now, by harmonic wave, well, we'll define it. Plenty of non-harmonic waves, but put a broader context later. Okay. Again. That's y equals a sine of kx. I almost wish I had put a cosine here, but that's all. Okay. Now t equals 0. What does the graph of y equals a sine of omega t sine of kx look like? Give you the hint, if t is 0, what's the sine of omega t? No. Circular model, sine is the projection onto the y-axis. Projection of the 0 vector on the y-axis is 0. Okay. So this is a pretty simple graph. Okay. Now, we have a little pause. I want to have a discussion of the unit circle. That's sine of 0, 0. It's easy to get turned around in that. Some days you just get turned around in things. And y equals a sine omega t. If omega t equals pi over 2, right? Then sine of omega t is 1. T, of course, equals pi over 2 omega. Right? Then you have, well, sure, again, I think I'm looking something like that. In there. Here's x. Of course, here's 1. And I put t in. See? I got the only one that gets some turned around someday. Break out comes wrong. I do it all the time, but I've got an excuse. Okay. So it's going to be just the same as I sine of kx, right? That's like I sine of kx, a sine of kx. See what I mean? Okay. So now, answer for me. For omega t equals pi, omega t equals 3 pi over 2, for omega t equals 2 pi. Okay, so now, pose the question, what would the graph of this function look like for omega t equals pi? If this is the graph for a sine of kx, right? This graph, sine, what's this function for omega t equals pi? And there it is, right? And here, for omega t equals 3 pi over 2, and here, for omega t equals 2 pi. And I have the class draw these, so they're much neater than mine. Okay, and I was hoping for that. Okay, so yeah, level here, and it's upside down here because the sine of 3 pi over 2 is -1. The sine of pi, the sine of 2 pi, sine of any integer multiple of pi, of course, is 0 because you're either here on the unit circle or here on the unit circle. And you're back here, and you're back here, right? Now, what happens in between? Okay, for what about for omega t equals pi over 4? Okay, got some good answers, very quick, which is good because we're almost out of time. Here's A, here's negative A. Here's A. Here's negative A. Here's A. Here's negative A. Now here, I have A and negative A. Okay. But your graph isn't going to come all the way up there, all the way down to negative A, because the sine of omega t would be the sine of pi over 4, which is square root of 2 over 2, which is about 0.7. So that the graph is going to look like, what happened to my blue chart? There it is. Graph is going to look like this. And go between here and here. Okay, so all the values, all the y values are going to be pressed down a little bit. So it'll look like that. So what's going to happen at t equals 0, that is flat. At t equals pi over 4, it's up here. At t equals pi over 2, it's all the way up here at full amplitude A. Okay. And then it comes back down to 0. And at 3 pi over 4, it's going to be down to this again, right? It's going to be down to 0. Then 5 pi over 4, it's going to be down this way, just a reflection of this. And at 3 pi over 2, it's going to be down here. Here's your picture. That's going to be come back up through the reflection of this at 7 pi over 4. And then back to flat at t equals omega t equals 2 pi. Now, of course, not necessarily interested in what omega t is. You notice the t is pi over 2 omega here, right? And here omega t is going to be pi, so t equals pi equals omega. And here t equals 3 pi over 2 omega, and so forth, right? So you can calculate the t's, but basically, if you know the frequency, this is at a quarter cycle, this is at a half cycle, this is 3/4 of the cycle, and this is at the full cycle. So if it's a tenth of a second, then this would be 0.025 seconds, fourth of a tenth. Half of the tenth would be a 20th or 0.05 seconds. This would be 0.15 seconds, this would be 0.015 seconds, and this would be 0.1 second, right? So whatever the frequency, however fast this thing oscillating, there you have it. Okay, that's called a standing wave. We'll see. We're out of time now, but We'll demonstrate some of these, but these are the mathematical descriptions. Okay.